multiplying polynomials, there's a few different cases. You have a monomial times a polynomial. So that's this first example. So this is basically distributing, multiplying that monomial times both of the terms in the polynomial. And so we'd have 4 times 3 would be 12. So I have 12. We have x squared times x to the third. So that would be x to the fifth. And then we have that y. We don't have any other y's to multiply by, but that's going to be included. And then we'll have 4 times -2, so -8. And then we have the x squared times the x, so that would be x to the third. And then we'll have the y. All right? So when we're multiplying a monomial times a polynomial, any kind of polynomial, just distribute to all the terms. Now, when you have a binomial times a binomial, then there's a couple different ways you can do this. I'm going to show 2 ways. I could show you a third one as well, but one way to do it is called double distributing. And so we take the first item, 7x, and we put it down, and then we take the whole second parentheses, and we're going to multiply 7x times that whole second parentheses, and then we take the 2 and then multiply that times the second parentheses. So you're going to basically double distribute. You're going to distribute in the case from of the 7x times that parentheses, and you're also going to distribute with multiplying the 2 times the second parentheses. So this gives us 21x squared. Make sure when you have x times x, it gives you x squared. And then 7x times 5 is 35x. And then 2 times 3x is 6x. And 2 times 5 is 10. Now the middle terms, these ones in the middle here, will add up often, not all the times, but they will add up and you can combine them. And so we have 21x squared plus 41x plus 10. All right, so that's one way to multiply by a binomial times a binomial. Now another way to multiply by a binomial times a binomial, and you would do this if you have just 2 binomials written together, so just like the last problem, or if you have a binomial squared. When you have a binomial squared, I'm just giving you a different variation of where you might see this. When you have a binomial squared, you don't just square each term inside. You have to write the binomial 2 times right next to each other, and then either use the method from before, the double distribute, or the FOIL method. So the FOIL method, you can see the anachronism FOIL, and it stands for firsts, outer, inner, last. And so the items that come first in each binomial are the 2x and the 2x. So we're going to multiply 2x times 2x, and that gives us 4x squared. And then we're going to do the outer terms, the terms on the outside of the expression. So 2x times -1y would be -2xy. And then we multiply the ones on the inside. So -y times 2x, which is again -2xy. And then you have the last items. So the last items are these ones that are coming last in the expressions in the binomials. So -y and -y come last in each of the binomials, so that becomes +y squared. Now you can combine the middle terms, these -2x's and -2x and -2xy and -2xy gives you -4xy. And so this is the final answer, 4x squared minus 4xy plus y squared. All right, and it's the same as if you double distributed. All right, so here's some additional problems. You can pause the video, you can try to do this on your own, and then watch the solution that I'll do in a minute. But a third way that you might do these, and I'll just show it briefly, is this. Make a box that has 2 rows and 2 columns, because we've got a binomial times a binomial. Put the terms from the first binomial along as row headings, and then put the terms from the second binomial as column headings, or you could switch that around, doesn't matter, but put the terms from one binomial as the row headings, and then the column headings from the other binomial, and then just multiply all the rows and columns together. So 3x times 2x is 6x squared, and then 3x times 8 is 24x. Oh, that is a really not very good 4. All right, there we go. And then -1 times 2x would be -2x. I'm having trouble writing. And then -1 times 8 is -8. So the final answer here, well, you can add terms that are in the diagonal. You see that these terms here in the diagonal, oops, I didn't mean to cross that out, but the diagonal terms are like terms, as they will often be, and so you can combine those. So we have the 6x squared we have positive 22x, and then we have the -8. So that should have been the answer that you got from foiling. Okay, these terms that are in the box should be the same terms that you have in this blank here when you did it by foiling. The order might be different, but they should be the same terms. And then the next example, all right, I'm just going to go to foiling. So -5x times x is -5x squared. So that's supposed to be a -5. I'm experiencing a delay with my computer in writing this. Outside terms are positive 35x. Inside terms, 2 times x is 2x. And then last terms, 2 times -7 is -14. So then we can combine our terms. Of course, there's nothing you can add with the 5x squared. And then you have 35x plus 2x. That would add up to 37x. And then you have the -14. So it should be -5x squared plus 37x minus 14. Now, I have an application problem here, and it says if one dimension of a square is increased by 2, while the other dimension is decreased by 2, express the rectangle's area in terms of the original square's side length. So I want you to imagine, okay, here's the original square I'm drawing, and let's call the original dimensions x. So I've got this square is x by x, and then I'm going to increase one dimension by 2. So I'll extend this out by 2 units. So put a 2 there. But I'm going to shrink the other direction by 2 units. So I've got to bring that down. So if I bring this down 2 units, so instead of x, we'd have basically x minus 2. Okay, so this is the 2 that we brought it down. Oops. So we brought this one down. I'll put a little arrow to indicate we brought that down, and we extended out one dimension by 2. So we'll stretch this out like that. Anyway, so the rectangle that is formed, I'll just draw this in running out of, I guess, blue, would be this rectangle. So what are the dimensions of that rectangle? Well, we added this 2 when we extended that out, so the answer would be x plus 2. Pause the video and try to FOIL it and see what you get. So the answer you should get is x squared minus 4. Because when you FOIL it, the middle terms, which are 2x or negative 2x and positive 2x, will add up to 0, and so they'll disappear. And so you just are left with x squared minus 4. Now what that means is no matter what size original square you start with, they could be 1,000,000 inches by 1,000,000 inches. If you subtract 2 inches from the original length on one direction and add 2 inches to the original length from the other direction, the area of this rectangle will always be minus 4. Because x squared is the original area, it's always going to be 4 square inches less than the original square's area. Okay, so if you try that and see if that's true. So like if you pick like 5 to be the original square length, so 5 times 5 is 25, so that's the original area of the square. But if you subtract 2, so that's 3 for one dimension, and add 2, and that's 7. So now you have rectangle that's 3 by 7, and you multiply 3 times 7, you get 21. Now 21 is 4 less than the original square's area. And that's what the formula is saying here that we just got. All right, anyway. Now, we also need to be able to multiply a binomial times a trinomial. And so if you have a binomial times a trinomial, you can again do it by double distributing. So we could take the first term, negative 2x, and we'll distribute it to all 3 terms of the trinomial. And then we'll take the second term, which is 3, and we'll distribute that to all 3 terms of the trinomial. And when you distribute the negative 2x, you get basically this first line. When you multiply the 3 times the trinomial, you get this second line. Now I've lined up the terms in columns of like terms. So now I can just add downward, and you see I get negative 2x to the third plus 13x squared minus 23x plus 12. So I would recommend that with a binomial times a trinomial that you double distribute, and then you can line them up vertically and get your answers. All right. Now another thing in section 10.6, and they're trying to prepare you for something that we're going to encounter later, but they talk about some patterns, special product patterns, and it's used when you have like a binomial squared. If you have a binomial squared, you would write it twice, like we mentioned before, and then one way to do it is you could FOIL it. But we're going to see a special pattern here in a minute in the box where we don't have to FOIL. We can just use that pattern. So if you have a plus b times a plus b, you're going to FOIL. So first terms multiply together. A times a would give you a squared. And then outside terms, so a times b. And then the inside terms, b times a. But b times a is the same as a times b. So I'm just going to write it alphabetically, a times b. And then the last things that are in each binomial, b times b, would be b squared. Okay, that's supposed to be a 2. Now, we can combine the middle terms. These can be combined, the ab plus the ab. So it's like 1ab plus another 1ab makes 2ab. So you have the a squared. You have 2ab and then you have b squared. So look at this pattern. When you square a plus b squared, you don't just get a squared plus b squared. You get a squared plus 2ab plus b squared. All right? So you square the first thing, you square the second thing, but then you also add this middle term, 2ab. All right? So here's an example. Suppose we have x plus 8 squared. So x is acting like the a. 8 is acting like the b. So you basically have a plus b squared. And so according to the pattern, it would be a squared, but in this case, x squared. And then the middle term would be 2ab. Well, a was x, so 2 times x, and then times b. b is 8 here, so I'm going to put in 8 there. And then lastly, we have, according to the pattern, b squared. So 8 was our b, so I'm going to put in 8 there. And so x squared, of course, is only written as x squared. And then here we can multiply the 2 times the 8 and get 16x. Trying to do a 6. And then 8 squared. Well, what is 8 squared? It's 64. So our final answer, x squared plus 16x plus 64. Okay, you pause the video and try this next example, 2x plus 7 squared. Don't do it by FOILing, try to use the pattern. So what you would do is treat the 2x as the a and the 7 as the b. And so we're going to do a squared, so 2x squared. So I'll put that inside parentheses. There's 2x. And I'm going to square that. All right, and then the middle term, we'd have plus 2ab, so it'd be plus 2 times a, but a is 2x. And then times b. Well, b is 7. And then last of all, we have b squared, so 7 squared. So this 2x squared becomes 4x squared. And then the middle terms, okay, 2 times 2 is 4, times 7 is 28. So you get 28 and then x. Okay, I scribbled out that term. I couldn't figure out how to erase it, but if we multiply these together, you basically get 28 x, and then 7 squared would give us 49. So 4x squared plus 28x plus 49. All right, and then the next example, we have a binomial a minus b squared, which would be a minus b times a minus b. So if we FOIL it, a times a is a squared. And then outside terms, minus ab. So I already put the negative sign in there. And then inside terms, also negative ab. So I put the letters in alphabetical order. And then last terms, negative b times negative b would be positive b squared. All right, so the final pattern is a squared minus 2ab and then plus b squared. So there's the pattern when you have a minus sign. The only difference between when you have a plus b squared and a minus b squared is that that middle term is not 2ab, it's minus 2ab. So then we can just apply this and go, okay, so I've got x minus 5 squared. Well, the a is the x and b is the 5. You don't even have to say negative 5 because the pattern will take care of the minus. You just say a is x and b is 5. So that would give us x squared and then outside, I'm sorry, then minus 2ab. So I'm going to put 2 and then a, which is x, and b, which is 5. Okay. And then plus 5 squared. All right, so then we have x squared and then negative 2 times 5 is negative 10, so we're going to have negative 10 and then x, sorry, and then plus 5 squared, so that would be 25. I'm sorry for the delay. Okay, so x squared minus 10x plus 25. Now the next pattern, I mean, here's a you try it problem. So if you can go ahead and pause the video and try that. All right, so we have 3x minus 4 squared. So you're going to do the pattern. So you're going to have 3x in parentheses And then we're going to have minus, because this is a minus situation, 2 times. Now 2 is just part of the formula. It's always going to be there. A, which is 3x, and then b. B is 4. Again, don't worry about the negative sign. The pattern takes care of that. And then last of all, plus b squared. So 4 squared would give us 16 in the end. I just want to write what you got. Okay, so now you can square 3x and you get 9x squared. And then if you multiply 2 times 3 times 4, you get 24. So this would be negative 24. Oh, there's such a delay. X. And then 4 squared gives you 16. Okay. So that's the answer. One more pattern. If you have a plus b times a minus b, you go a times a. That again would be a squared. I just can't write a 2. Outside terms, negative ab. Inside terms, positive ab. And then last term, b times negative b would be negative b squared. Now notice we have a negative 1ab and a positive 1ab. These will add up to 0. Okay, so they'll basically just get crossed out because they add up to 0. And then we'll just have a squared minus b squared. All right, now that is called a difference of squares, a squared minus b squared. And that only occurs when you have a plus in one parentheses and a minus in the other parentheses. Now it could start with minus and then have a plus, or vice versa, it doesn't matter, but you got to have one positive and one negative. So here, using just the pattern, we see they have plus and a minus, so it's just going to be x squared and then minus 9 squared. So you'll have basically x squared, of course, and then minus, well, 9 squared is 81. So that's the answer. Okay, here we have 2x minus 7, 2x plus 7. So one's negative, one's positive, so this would fit the pattern. So you can go a squared minus b squared, so you get 2x squared minus 7 squared, which of course is going to be 4x squared and then minus 49. You can try the next one, pause it, and then I'll show the answer. So 5x plus 2 times 5x minus 2, you have a plus and a minus, so we could write it as a couple set of parentheses, and then put 5x, oops, and then we'll square that, and then minus 2 squared. So 5x squared is 25x squared And then you have 2 squared, of course, which is 4. So 25x squared minus 4. All right? So let's look at the last item here. Dividing a polynomial by a monomial. So here, these are all worked out for you. So you see that if I'm taking a polynomial, like this polynomial here, and you're dividing it by 2x squared, well, you can just write each term of the polynomial and put it over the monomial. So you can see how I did that. Then you can reduce, okay? So when you reduce here, the the 2's will cancel, the x squared will cancel with 2 of these x's and make this just a 1. And then in the next example, the x squareds cancel, and then the 2 inside of 6 can be canceled, and it leaves a 3. And so you have x minus 3, because there's nothing left in the denominator. But in the next problem, one of the x's cancels, dropping that down to just an exponent of 1. And the 2 cancels that's inside of 10. And it leaves 5 on top. And so, but the problem is you still have an x left over in the bottom. And you can't just pop that up to the top or anything like that. You've got to keep it in the bottom. So the answer is x minus 3 plus 5 over x. Another example, we have this polynomial divided by 6xy. So just put each term over 6xy. And you see that I did that. And then I reduced, and I got 5xy over 2 plus 2 minus 3 over y. So some things don't cancel in the bottom, but you'll just have to, leave it the way it is. And so that's the answer. All right. Now we're going to just look at factoring of polynomials, but just the first step, just the first thing with factoring of polynomials. And so what you have to do here is basically just distribute out the common factor. Now, you notice that first I looked at a problem with just numbers. So 12 is 4 times 3, but 4 can be broken down further into 2 times 2. And so your final answer is 2 times 2 times 3. That's called the prime factorization of the number 2. So when you factor a number, you're basically breaking it down into its factors. It's the numbers that multiply to give you that. Now, when you're factoring a polynomial, you're breaking it down into polynomials that multiply to give you that original polynomial. Now, let's look at the forwards and backwards here. So if you were having to multiply the monomial 3x times this binomial, you would distribute, right? And so that would be considered to be multiplying, because you're multiplying the 3x times everything inside there. Now, the opposite of opposite of distributing is just to distribute out a term. And so you see here that I've got 3x squared plus 6x, and each term there is divisible by 3 and has an x in it. So it's divisible by x. So my greatest common factor is 3x, and I pull that out just like doing the opposite of distributing it in, and I get 3x times x plus 2. And you can see that if I distribute it back again, I get the original value. So factoring out is just the opposite of multiplying the factor into it. All right. Now, factoring out the greatest common factor is a skill that's very important. You have to find a factor that's common to all the terms, not just some terms, all the terms. Now you can see here that 5 is a common factor of 5x and 45. So if I divide the first thing by 5, then and also the second thing by 5, so 5x divided by 5 would be just x, so that's what would be left over inside there. And 45 divided by 5 would be 9. So you can figure out what would be left that goes inside the parentheses just by dividing. All right, now here in the next example, the numbers are a little bit higher, but you have to find the greatest common factor. So what goes into 24 and 42 that's the largest possible number? Well, 6 does, okay? But it gets a little harder the larger the numbers. Now, you have 3 y's here, and you have 2 y's here. So I can pull out 2 y's out of both terms. I can't seem to write an exponent of 2. Okay, so that's 6y squared. All right, and I can distribute out 6y squared out of each term. Now remember, it's like dividing. So if I was to divide the bottom here by 6 and then y squared, like that, 24 divided by 6 would give me 4. And y to the third over y to the second, 2 of those y's would cancel, leaving just a single y. So basically be 4y. And then if I divide this second term by 6y squared, and I can't write it, but 6y squared, and this would give us -7, and y squared divided by y squared would just be no y's at all. So it would just be 6y squared times parentheses 4x minus 7. Okay, and you can read my note over here on the right. And then the next example, you have 60z to the 5th plus 60z to the 5th plus 132z squared, z to the 3rd. Now what I did here is I broke up 60 and 132, into its prime factors. All these numbers are prime numbers, so we're broken it down as much as we can. And then we can look and see what factors are common to both expressions of factors. So 2, 2, and 3, 2, 2, and 3, those numbers are in each of the prime factorizations. So the greatest common factor, you can figure that out this way, would be 2 times 2 times 3, which is 12. So 12 is the greatest common factor for the numbers. Now, as far as the z's, I have z to the 5th times z to the 3rd. So remember, it's the lower one that limits you. So it would be z to the 3rd would be your variable common factor. So 12z to the 3rd. And then if I divide 60 by 12, I have 5. And I take 3 z's away from 5 z's, and I have 2 z's, so 5z and then squared. And then if I divide 132z to the 3rd by 12z to the 3rd, well, I would just get 11 because the z's would disappear. Now, interesting thing to note is you notice that 2, 2, 3 was the greatest common factors, And look what's left over that wasn't in the greatest common factor, 5. And that's what ended up here in this. And then the 223 was taken out of this. Well, what's left over is the 11. So you can just, use the extra numbers that aren't used in the greatest common factor as what's going to be remaining in the parentheses. All right, so then this next example, if you think about this, okay, what's the greatest common factor for the numbers? Well, obviously 3 goes into everything, but because this first term is negative, it's the highest power term and it's negative, I'm going to actually distribute out a negative of that greatest common factor. But it has to be in everything. You can't use 9 because 3 is not divisible by 9. Only 3 goes into all three numbers, 9, 18, and 3. All right, so then if I divide negative 9 by, okay, let's think about the variables. So 8 to the 5th, 8 to the 3rd, 8 to the 2nd. So 8 to the 2nd is the highest number of A's that can be distributed out of all three things. Remember, it's the one that has the least that limits you to how many you can do. So I can only do 2 A's, so it'll be A to the 2nd power. So my greatest common factor is, can't write it again, is negative 3A squared. So I'm going to divide everything by negative 3A squared. So negative 9 divided by negative 3 would be positive 3. And if I take 2 A's away from 5 A's, it'll be 3 A's. So I'll have 3A to the 3rd power. That's a 3A to the 3rd power. And then 18 divided by negative 3 would be negative 6. And I'm taking 2 A's away from 3 A's, so I'll just have 1 A. And then last of all, negative 3 divided by negative 3 is positive 1. And I take the A's away because I'm taking out two A's. And so I just have positive 1. Now notice that you don't end up with 0 here. You end up with 1. All right? So if the leading coefficient is negative, then distribute out the negative of the GCF. All right? And then the last example here has, not the last example, but this next example has 2 variables. So we don't just have x, but we also have y. So what goes into all 3 terms? 18, 12, and 84. Well, you could break up 18 into its prime factors. You could think of it as, okay, 2 times 9, but 9 breaks up into 3 times 3. So basically the prime factorization of 18 is 2 times 3 times 3. 12 is 4 times 3, so that's 2 times 2 times 3. All right, and then last of all, 84. Now 84 is 12 times 7. And so 12 would give us the 2 times 2 times 3. And then you also have a factor of 7. So 2 times 2 times 3 times 7. So your greatest common factor, well, I don't have 2 2's here. So I can only use the GCF of 2 times 3. That would be my greatest common factor. So 2 times 3, which would give us 6. So the greatest common factor is 6 as far as the numbers. Now, x's. How many x's are in each of the terms? Well, this one has 4, this one has 3, this one has 2. It's the one that has the least that limits you. So I would only I'm only allowed to have 2 x's in my greatest common factor. All right, how many y's? Well, you have 3 here, you've got 2 here, and you got 4 here. So this one limits you to only having 2. So 6x squared y squared is my greatest common factor. And so if I divide 18 by 6, you get 3. And then I take 2 x's away. That leaves me with just 2 x's left over. And then 2 y's pulled away from 3 y's would leave me with just 1 y. Then if I divide negative 12 by 6, it would give me negative 2. Now I've already got the negative sign there. And then I take 2 x's away. That would leave me with just 1 x. And then I take 2 y's away from 2 y's. Well, there won't be any y's. And then I divide negative 84 by 6. That gives me 14. And then I'm pulling out 2 x's from 2 x's, so there won't be any x's. And then I'm pulling out 2 y's from 4 y's, so that would leave 2 y's left over. So that's my answer. You have the greatest common factor times 3x squared y minus 6x minus 14y squared. Now, there's 1 or 2 problems in the homework that have fractions, and so let me show you how you can do with this. Now notice that the denominator in each of these fractions is 5. You have a denominator of 5 for each of these fractions. So that tells me that you could distribute out 1/5. Now you need to realize that 2/5 is really 2 times a fifth. 2 times 1/5 is the same as 2/5. So I could think of this as 2 times 1/5. And 3/5 I could think of it as 3 times 1/5. And 1/5 could be thought of as 1 times a fifth. So I've got this 1/5 in each of the expressions, as well as b's and c's. I have at least 1 b and 1 c in all 3 terms. So my greatest common factor will be 1/5 b and c. So if you pull that out, it's like just crossing, canceling it out. And so you'll just have 2b to the first, c squared, and then minus 3, and then a 1b left over after you pull a b and a c out, and then minus 1. So you wouldn't end up with 0, you'd end up with a minus 1 that we have remaining after these are all, crossed out. All right. All right, so then we distributed out the 1/2 or 1/5 BC, and we end up with these terms. Now, little note here for next week. For many factoring problems that we'll encounter next week, you'll have to correctly distribute out the greatest common factor first. Make sure you do that step, and you need to do it correctly. If you don't distribute out the greatest common factor first and do it correctly, then what you have remaining inside the parentheses will not be correct, and therefore you will not be able to correctly factor the rest of the way. All right.